Okay, so let's pick up where we left off last time. So we spent ages talking about the background, thanks Saskia, to the photoelectric effect. And we kind of put it in a historical context, but today is all about simply understanding just the photoelectric effect in its entirety, in all its detail, with no kind of distractions along the way. So what I've drawn on the board is the basics of what's happening. So we've got a charged piece of zinc, and the reason that it's zinc is because zinc works, Isaac, well with the colors of light that I happen to have available to me in the science lab. So there's nothing special about zinc. It just works well for the demonstration that I'm doing for you here in school. And we're shining on a photon of, actually, it's UV light of a particular frequency. And remember, the word photon is the word that we're now going to adopt to switch pictures in our head, that instead of light being a continuous wave of energy, if we were capable of seeing the light as it really is, what we would see instead is not a continuous stream like water coming from a hose pipe or something like that. It wouldn't be a continuous stream. It would be more a collection of multiple small objects all traveling very small together, which actually I suppose you could argue a stream of water is if you get down to the level of the water molecules, but more kind of bullets flying from a machine gun. So lots and lots and lots of tiny little localized packets. So this is just a single photon has just weaved its way in. For historical reasons, photons are always drawn with this wiggly line. It's confusing, I think, because it makes it look like it's a wave, which we're trying to get away from. But yeah, the photon comes in and it's absorbed by an electron, which is ejected from the surface of the metal. So I'm just going to repeat the demo for you because you can't see it enough times to make sure that you understand exactly what's going on, because this takes right to the heart of the quantum mechanics. So let me switch to the other camera. Okay, so here we've got our piece of zinc again, which again I've scratched off the oxide layer, and it's sitting on top of the electroscope, and at the moment you can see that the leaf is down. And now all I'm going to do is just charge it up with some electrons. I'm just going to drop the negative terminal of the power supply onto that. And so all that's just done is just deposit a load of electrons onto the piece of zinc. And now it looks like the picture that I just drew on the board. We've got a piece of zinc and it's got additional electrons swarming all over the surface of it. And now what I can try to do is to release those electrons using some energy from some visible light. And you'll notice that the electrons are not being released. The electroscope is not discharging. And this is contrary to what the wave theory of light would suggest. The wave theory would accept that ultraviolet light is more energetic than visible light. But the wave theory would say, well, it's a continuous stream of energy. So 5 seconds of UV is kind of just 10 seconds of visible light. It's the difference, you know, between a dripping tap and a tap turned on full. It's still sending energy. If you wait long enough, even a slow running tap will fill up a bucket. That's not what's happening. The visible light is shining down onto the zinc. It's delivering energy, but it is not releasing any electrons because fundamentally the wave theory is wrong. The light is not arriving as a continuous stream of energy. The light is arriving like bullets from a machine gun. And the poor little visible light is composed of pathetic little bullets that do not contain very much energy. Whereas, bring in the UV, here it is. When I put the UV on straight away, you can see that the leaf just goes down, 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 as electron after electron after electron is released from the surface of the zinc. Instant, didn't have to wait. It started discharging immediately, and this is because every single photon of light in the stream from the UV, every single one of those photons contains enough energy to release an electron. Let me put the camera back so you can see the board again. Okay, so we're going to work our way through a set of key ideas here. So the first one is that thing number one, it's 1 to 1. One photon releases one electron. Now, you could argue statistically that it's not a zero probability impossible event that one electron should be hit by two photons. It's not impossible. It could happen. But electrons are very, 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 very small. And photons are even smaller. And if an electron gets hit once, it is far more likely to move a little bit for a fraction of a second and collide with something, an ion or another electron, or interact with another piece of matter and lose that energy that it's just been given. It's much more likely that that will happen than it sit there and keep its energy that it's just been given until a second photon hits it. So the visible light photons, which are not enough, they don't contain enough energy to liberate the electron. You could argue that if we just wait long enough, surely one day, once upon a time, an electron will get hit by two photons before it loses the energy from the first photon. It'll get a second lump of energy from a second photon, and it will release the electron. And I guess that's true. I reckon that if I left that, maybe I will over the weekend, if I left that thing charged over the weekend and I gave it days and days and days to discharge, would it have discharged by Monday morning? Maybe, but even then it would probably be because the air is transferring electrons from the surface bit by bit by bit rather than the light. So in all meaningful ways, unless one photon can release the electron, two photons aren't going to do it, because the electron will just have lost the energy from the first photon before a second photon hits it. So that's the first thing about the photoelectric effect. One photon releases one electron. Second thing, the electron is bound. Okay, so electrons are negative. The nuclei forming the metal lattice are positive. There's a force of attraction. The electrons are bound. You know in a metal that some of the electrons are delocalized and can roam throughout the metal lattice, but they can't leave the metal lattice. They're still electrostatically attracted, and they are bound and they can't go anywhere. So you could ask the question, well, what's the minimum amount of energy that's required to let it leave? So you would need to think about the work that would need to be done to apply a force over a certain distance to wrench that electron away from the positive attraction of the metal lattice. Now, we do actually do calculations like that a little bit in year 13 when we're talking about liberating a piece of matter from a planet's gravitational field. So we will actually return to this idea. But you can accept that there will be a certain minimum amount of energy that if you give it to the electron, it will just allow the electron to break free. And this electron that does break free with the minimum energy, you should note it will be a surface electron. There'll be loads of electrons all the way down through the piece of metal. And it might be that a photon finds its way 0.5 millimeter or so inside the metal before it collides with an electron. But those deeper electrons will require even more energy than the minimum. The absolute minimum is going to be a surface electron, an electron that is right at the top of the metal, begging to leave, probably with a little bit more kinetic energy than most of the other electrons, right on the verge of being able to leave itself, but still bound ultimately. That's the minimum that we're talking about. And it's got a special name. It's a bit of a weird name. It's referred to as the work function. So this is the absolute minimum that is required, which means number 3, the photon must have at least energy equal to phi. And if it doesn't have that energy, it just cannot leave. That is the minimum amount of energy that is allowed. Now, if we do give it that minimum amount of energy, that poor little electron will be released from the surface and have nothing left. It just won't be able to move anywhere because we didn't give it any energy left over for its kinetic energy to actually move away from the surface. So in actual fact, if we give it more than that, if it has more, then we've got this relationship that E will equal phi plus some kinetic energy. So I'm just going to tweak that in a second, but that's a really important formula. That's one of the big formulae from this topic. So I'm going to put that in a box in a minute. I just need to tweak it a little bit. Say a photon does come in that's got a little bit more energy than the work function, and there's a little bit left over from the kinetic energy. If we were to monitor the electrons coming out, so there's one electron, if we waited for another electron and another electron and another electron and another electron, it's important that you realize that they wouldn't all come out with the same kinetic energy because only some of them will be surface electrons. And quite a few of the electrons that are going to be released will actually be electrons from a little bit deeper inside the metal. And they will have had to have been paid a little bit more energy than the work function in order to release them. And so their surplus of energy isn't going to be quite as big as the surplus of energy that a surface electron will have. And therefore, this kinetic energy here is actually a maximum kinetic energy. Plenty of electrons will come out with less kinetic energy than that because they will have not been surface electrons and they'll have had to have used a little bit more energy than the work function in order to escape. So this equation here, sometimes referred to as the Einstein relation. Remember I told you last lesson that Einstein used the photoelectric effect to really run with the idea of the existence of photons. And it was actually for his work on the photoelectric effect proving or justifying the existence of photons that Einstein actually received his Nobel Prize for, despite the fact that the very same summer, Einstein published work on the existence of atoms by explaining something called Brownian motion, which we'll talk about next year. And also he published his ideas on special relativity, which revolutionized our thinking about space and time and speed. So he did a lot. He had a good summer that year, 1905. But it was this that he got the Nobel Prize for. And I think probably part of that was because people understood this, whereas they found the photoelectric, they found special relativity just a little bit out there. And they found that the existence of atoms was a little bit of a dangerous idea. People had conjectured it for such a long time that it was, people were very tentative about accepting proof of their existence. Whereas this is kind of very easy to demonstrate and explains away a whole load of problems which were threatening to undermine this glorious edifice that physics had become. Okay, so the photon must have at least that much energy, and this is our very important equation that we're going to be using a lot over the next couple of lessons. Which brings us to point number 4. How much energy does a photon have? And so this brings us to our second equation, which technically is Einstein's work, but it was proposed, at least in form, by Max Planck when he was dealing with atoms. And as I told you last lesson, he just didn't quite understand the importance of what he'd been suggesting. So tends to have Planck's name associated with it, but I think largely it was Einstein that saw the significance of it. Einstein provided a link between how we had traditionally been describing light in terms of the frequency of an electromagnetic wave. He provided a link between that frequency and the energy of a single individual packet of energy of that light. And he basically stated that the energy of the photon is directly proportional to what we have been calling the frequency of the light. Double the frequency, that means that twice as many peaks will be arriving in a second, which means twice as much energy will be arriving in a second. But he's already said in his special relativity that light always travels at the same speed. So if you are going to double the frequency, how are you going to get twice as much energy arriving if all those photons are traveling at the same speed? They can't get there twice as fast by traveling, because they don't travel twice as fast, they travel at the same speed. And he's adamant that you don't get twice as many photons. He's relating that idea to intensity, and we'll come to that in a second. Intensity is a related concept, but he wants to pin it down to the individual photons, not the number of photons. So he's saying that if doubling the frequency means twice as much energy arrives per second, then it means each photon must have an energy associated with its frequency. It must be directly proportional to its frequency. And he actually put in a constant of proportionality there, and he called the constant of proportionality H, and that is known, or I think he made sure it was called Planck's constant. You know, every time I write Planck's constant, I have this little moment where I can't remember if there's a C in it or not, but I'm pretty sure there is. Okay, so this is your second equation. There are only 3 equations in the quantum physics topic, and there's 2 of them right there from the photoelectric effect. You are going to be using this equation a lot, and this one quite a lot. So make sure you've got them both clear in your head, which one's which. So basically, the idea is if the frequency is high enough, the energy will be high enough. And in particular, it needs to be higher than phi, the work function. And if it is, electrons will be released one at a time, because one photon releases one electron, which means that if the frequency is high enough that the energy is actually higher than the work function, it won't be allowed to release more than one electron. All of that energy goes to the one electron that absorbed it, and therefore that electron will have some leftover energy, which will be its kinetic energy. But remember, the kinetic energy is a maximum because some of the electrons that are released will require more energy than the work function because they're a little bit deeper in the metal, and so they require a little bit more energy than the minimum in order to release them. Okay, one more thing, which I've kind of run out of space there, but I'll do it down here. Now, the intensity is the amount of energy that's arriving per second. You remember that from the waves topic. And or the power per meter squared, isn't it? So there's an area in there as well. But it's about the rate at which energy is arriving. Now, in the photon theory, what Einstein says is that if you increase the intensity, what you mean is you're getting more photons. You do not change the energy of the photons because the energy is related to the frequency. And just because you turn the brightness of the lamp up or move the lamp closer, you don't get a change in frequency. When I have this lamp, there's the lamp. If I bring it nearer to the camera, you get higher intensity, and I take it away, you get lower intensity, but the color of the light doesn't change. That's because the intensity doesn't control the frequency, and therefore it doesn't control the energy of an individual photon. Nor can the photons travel faster, because Einstein's already said that the speed of light is fixed. So if the photons can't travel faster, and the photons can't have more energy themselves, well, if you've increased the intensity so that more energy is arriving every second, you must have more photons, which means more released electrons each second. Now compare that to what the wave theory would say. The wave theory says it's a continuous stream of energy, and therefore, if you turn the intensity up, you are increasing the rate at which the energy is arriving, and therefore you will fill up the bucket quicker. You'll have to wait less time to release the electrons. But we saw that that wasn't true. No matter how long we wait with the lamp, it never releases the electrons. Increasing the intensity doesn't make a difference. And indeed, when we put the UV on it, it didn't make it happen any faster than instant, because it instantly the leaf discharged. So what you do get is more electrons, not faster electrons, just more of them. They still come out with the same maximum kinetic energy that they had before, because it's 1-to-1, and each photon has still got the same amount of energy that it's always had. That board's worth of explanation is incredibly complex and difficult. Now, I've tried to do my best to lay it out for you in little tiny steps that are logically connected together. And so I'm hoping, if I've done my job right, then you will have just understood what I just said. However, that is a world away from putting your notes away so that you can't see them and reproducing the explanation yourself. having it in your head so that you can articulate it is even harder than listening to me articulate it and try and understand it. And that's your goal. I need you to be able to take a blank piece of paper and do what I've just done in the last half an hour. I need you to be able to set out the steps to explain to me why the photoelectric effect, which is the release of electrons from a charged surface, why the photoelectric effect requires the existence of photons, and why it cannot be that light is a continuous stream of energy that the wave theory predicts. If you can do that tomorrow, having slept on it for a night, then you properly should be impressed with yourself. I will be impressed with you if you can do it first time tomorrow. More likely, you're going to have to take a number of goes at this to get it right, and then you'll miss a little bit out each time, and then you just have to peak and then try again and again and again. In order to try and help you with it, what I'm going to do in a second, when the meet closes, is I'm going to post this video, and I need you to watch it a couple of times, maybe, over a period of maybe leave a day, then leave a week, then maybe leave a month, to leave a little gap to make sure that you understand it, not just in the moment, but long-term in your brain. And also I'm going to post an online simulation, an applet, where it shows you the photons and the electrons, and it allows you to judge the kinetic energy by allowing the electrons to travel through a gap where there's a negative plate pulling them back again and a positive plate repelling them. So you can get an idea for how much energy they've got by how far they managed to fly through this, this field that's pushing them back where they came from. So I'll put a little applet on so that you can play with this, but really, I just need you to learn how to explain it. So I'm going to actually finish the meet bit now. I'm going to leave the meet running, but you need to go away and you need to understand that, and you need to be able to reproduce that. And I'm going to be here for the next half an hour or so. So if at any point you get stuck and you want to ask me any questions, you can do so. You can have a play with the applet. I'll post a link in a minute. And if you don't understand that, you can come back and talk to me and ask me. But basically, your job for the next half an hour is to understand that and be able to reproduce it on a blank piece of paper. Right, do you want to ask me any questions?
Sir?
Yeah.
When we're talking about like the energy in a photon, is that radiant energy?
So the energy of an individual photon is literally a packet of energy. So it'll leave the source and it'll be absorbed by the electron. And as it travels, it's a localized little packet of energy. And you should just think of it as that and no more. It just travels from A to B in a straight line at the speed of light, little packet of size h times f. Oh, I should probably give you the value for h actually in a second.
But like, how does that energy like actually get absorbed by your electron?
Yeah, so Richard Feynman, the great physicist, he would say, you shouldn't go asking awkward questions like that. How rude of you. Clearly, the photon did exist, and then the photon didn't exist, but the electron was free and had a lot of kinetic energy. What more do you want to know? Is what Feynman would say. Nobody knows, fundamentally. We're not at that scale where we can ever observe, even in principle, a photon being absorbed by an electron. So we write equations that model the variables before the interaction, the variables after the interaction, and we have to accept that philosophically, in principle, we cannot know what happens during the interaction itself because it's unobservable in principle. And so we have to accept that there's a limit to what we know. It's not very satisfactory. And In fact, quite a lot of quantum physics took so very long to be accepted by the physics community, simply because fundamentally deep down, most physicists don't like quantum mechanics. It makes them feel uncomfortable. It reveals things about the universe that they would rather not know, like that there are limits to, in principle, what we can know. And if you do enough about quantum physics, it introduces a whole load of statistics in that you can't say for certain what will happen. You can only say, well, there's a 72.4% probability that this will be the outcome. Physicists really don't like that. They deal with certainties, and it makes them uncomfortable, quite a lot of quantum physics. And the question you just asked, it's just your first step towards that feeling of unpleasantness that's at the heart of quantum physics. Read around the subject. There's loads on the internet, and there are loads of popular science books that have been written by cutting-edge leading physicists, leading in their fields, and they've had a whole editorial team polish it and make it understandable for the layperson, i.e. the person who's not got 20 years worth of professorness of quantum physics behind them. Yeah, go on Amazon and in the popular science section, find a book on quantum physics and have a read. Much better to do it that way than to just randomly Google stuff, because there's a lot of stuff out there that's not correct. Quantum physics is very, very widely misunderstood by a great number of people. And so you want to make sure that you know who your source is that you're reading, because quite a lot of stuff on the internet is rubbish. However, the Wikipedia article on quantum physics has been peer-reviewed by physicists. So you're all right with that. That particular Wikipedia article is fine. Any other questions? Yeah. Any other questions about what's on the board? Okay, so this is just lesson 2 of the topic. We've got plenty of time to talk about the weirdness of quantum physics. But for now, your job late on a Friday afternoon is to fix that in your head.
Okay, so what is H then?